As you can see, this is the steam power cycle problem. So here we have the schematic, and this is the TS diagram. So a steam power plant operates on the cycle shown here in this figure. You can see this is the boiler, this is pump, condenser and turbine. So we already discussed actually the steam power plants and steam power cycle. So here actually you see all the required information given, and it says if the isentropic efficiency of the turbine is 87% and the isentropic efficiency of the pump is 85%. So that's the two important information given, the turbine efficiency and the pump efficiency. We need to determine the thermal efficiency of the cycle, so that we will calculate. So this is the first part of this problem, and the second part is the net power output of the plant for mass flow rate 15 kg per second. So enthalpy is given for point 3. At this point the enthalpy is given, so we do not need to calculate that one as well. So what we need to do, guys, here is the steam power cycle, which is specified with the turbine and the pump. So we need to determine the thermal efficiency of the cycle and the net power output. So we'll assume that this is a steady flow device. Okay, so a steady operating condition exists here, and we will consider all the kinetic and the potential energy changes are negligible. So if we write down all the assumptions, so let's say if we write down the assumptions, so we can say this is a steady flow device, okay, or the steady flow exists here. And the other thing we can say that the kinetic and the potential energy change, it is negligible, so we said it is very close to 0. Right, so we'll tell that okay, this is a steady flow components and operates on the Rankine cycle. Here actually the first part of this problem is, if you see, guys, we need to determine the thermal efficiency of the cycle. So what is the thermal efficiency? If we look at the first part, the thermal efficiency, it is actually the ratio of the net work output and the heat input. So we can write it down like this: thermal efficiency. Let me write it down here. So we'll define thermal efficiency, let's say eta, and thermal, say TH. So it is equal, we'll say, the net work output over the heat input. So this is actually the whole information. That's actually the first part of this problem we need to calculate. So here I will try to show you a flow chart like this. So if I say it is actually the net output is W net and the heat output is Q in. Okay, if I write it like this, so what we know from here is, if we actually want to calculate this thermal efficiency, at first we need this the net work output and then the heat input. So what I'm going to do is, I will write down the formula here at first. Let me write down in different color. So this, it is actually the W net over Q in. So if we want to get that, we actually need this net work, okay, the net work output. And here actually we have the work, you see the pump, so work in for the pump and the work out for the turbine. So the difference between these two, this is actually the net work output, isn't it? So we have the heat in for boiler and heat out for the condenser. So that's the separate thing, but only the work input is here, this is the work output. So this difference we can write it as equal, the W for turbine, okay, turbine minus the work for pump in, and for turbine it is out. So that means now what we need to do, guys, we need to calculate these two things, the work output for the turbine and the pump. and we know the formula. If I write down in a separate piece here, maybe that should be great. So let me write down like this. So eta efficiency, I will write it quickly. So this is the net work output over the Q in, and the net work output, we know it is the work for turbine. This is actually the output minus the work for pump. This is the in. Then what is the the work output for turbine? So work output for turbine, the work output for turbine, it is actually, we can write it is equal the efficiency, the thermal efficiency of the turbine into Ws turbine out. Maybe you are wondering that okay, how I got this formula. Let me write down the formula, especially when it is the efficiency. We know the efficiency formula, efficiency for turbine, this is equal the Wa over Ws we discussed earlier, and efficiency for pump, it is Ws over Wa. Right, we discussed this earlier, so you already know that okay, we have this formula. So when it is for turbine, so this is for turbine, so we can write this W output, the work output Wa, it is equal eta T into Ws, so we write that way. Now we need one more thing. We know the net work output, it is equal the W for turbine, work output for turbine, and the work output for input for pump. So that means now we need actually the pump. Okay, so we can write the work output for work input for pump. So we can use this formula from here. So for pump we can write so the work in pump in, it will be the Ws, the pump in over the eta P. So this is actually the direct formula, this one. So that means the first thing, guys, if we want to calculate the efficiency, then we need network output. To get the network output, we will calculate that work output for turbine, work output for pump, work input for pump, and then we will get the efficiency. So that's the overall flowchart for this problem. You know what I mean? And finally, so let's start with the problem. Let's start with the solutions. So if we calculate the work output for the pump, so we can write it is, now I will write clearly, pump work input. This is pump work input. So we can clearly write, let's say Wp in, it is equal the Ws pump in over eta P. And from the formula actually for pump, we know the formula is the specific volume and the pressure difference. Here pressure difference P2 P1, because we have, you see, so water, so this is actually the pump, and water is going from this point 1 to point 2, so the pressure difference, and you see the work is coming here. So when you will water is actually, if you look here, this is the low pressure zone here, and at point 2 this is high pressure. So you are trying to put the water into from low pressure to the high pressure, so you need some work input. So that's the work we are getting here. So when we are getting that work, and we know actually if we calculate this pressure difference into the specific volume, then we will get the the work. So that we know this formula already from the theories. I discussed it earlier. So this is actually the formula here. Now this specific volume, we will calculate this specific volume from table A5. So from table A5, Okay, from table A5 we can calculate it. If you look here, here actually if you look at this TS diagram, so the water, we it is actually the compressed liquid. If you see, this is the dome, here this is the mixture region, this is the superheated region, and this is the compressed region. So water here in the compressed region, so we can approximate the compressed liquid as a saturated liquid at given temperature, right? So at 38 degrees centigrade temperature, it is given 9 kPa pressure, so we'll approximate it as saturated liquid, and we will just use the table A5. So from table of A5 we'll get the V1. I'm not showing you because you already know. Okay, if you actually want to see table A5 and the pressure table, here it is 9 kPa, so it should be in between these two value. It should be in between these two value. This is for the in the specific volume for saturated liquid. So you can see it is you can see it is 0.001, 0.001 point something. So in between the value we'll get it. So I will write down it is actually 0.001009. Actually it is meter cube over kg. So what we need to do is we need to just substitute this value here. So let's do that, and it will be 0.001009, and pressure P2 is see from the formula, this is, it is given, it is 16 MPa, and here we will convert this 16 MPa into kPa, so it should be 16,000 and it will be 9. So we just converted MPa into kPa, and the efficiency for the pump, it is given, if you look at this, for efficiency for the pump it is given 0.85 or 85%, so we can write it at 0.85. Then we'll get the pump work input is 19 kilojoule per kg. So this is actually the the pump work input we got. So now what we will do, we have done with that, we will calculate the work output for the turbine, for the turbine. Yes, so now let's calculate the turbine work output. So the turbine work output, it is if you see the turbine work output, it will be we know the formula already, it is eta T and this, so we'll write it down. Let's say W T or V output, it is equal the eta T, this is for turbine, and the work WS turbine out. So actually when it is the turbine, you will see if we calculate the enthalpy difference. So this is the turbine here, and before so we have, this is the 0.5 and 0.6. So if we calculate, we discussed during the lecture when I discussed the theories. So if we calculate the enthalpy difference between this these two cases, so here actually it will be this is, you see, WS, we know it is for the actual cycle, so it will be the difference 5 and this 0.6s, so not 5 to 6s, because it is, you see, for the actual turbine cases. So now we can write it like this, eta T, and it will be has 5 minus has 6s. So now actually we need to do a lot of calculations for this section, guys. If you look, this has 6s, it is actually in the mixture region. It's inside this dome, it is the mixture region. So when it is the case, then if we actually want to calculate the enthalpy, we actually need to do some calculation, we need to use the table. But the one thing we can say here, actually at this section, it is the isentropic process. So the entropy for this 0.5 and entropy for this 6s, it will be equal. Okay, so now what do we need to do? We know the formula. I will show you. At first we need to calculate the quality. This is very important. So from now onwards, if when you will solve any problem, you have to do it again and again. So let's do that. So we'll calculate the quality. You know the quality formula. It is actually the x. We'll calculate for this point 6s. So x6s, it will be the s 6s minus sf and sfg. So from table A5, we can you know so for point 6, the pressure is 10 kPa. Go to the table 5. Okay, so let me show you table 5. Yes, it is table 5. So for 10 kPa, we are talking about the entropy. So this is 10 kPa. Look here. So the entropy, you see the SF, this is the value. SFG, this is the value. For SG, this is the value. So we need to use these values. I will just, to save some of your time, I will quickly put, all those values here. So what we know is F. So let me write it down like this. SF, it will be 0.6.92. I already showed you. And SFG, it will be 7.4996. How we got it? From table A5. So now I told you that this S6s, it is equal to S5, because you can see this is isentropic process. Isentropic means no entropy change. So now we can we actually need this x6s, and if we calculate S5, then we can write, okay, S5 equal this. So for S5, we see the condition is given 15 MPa and 600 kPa. And if you clearly look this point, it is actually in the superheated region. So that means for this section, if you want to calculate the entropy here, we need to use table A6 because it is in the superheated region. So from table A6, we can write, S5, or you can say it is X6s, for 15 MPa and 600 degrees centigrade temperature, the value, it will be actually 6.6796. I can show you from here. Yeah, you see this is for 15 MPa and 600 kPa pressure. So you can see the entropy is 6.6796. So that we got it from the table. So now we got all of this. So you look here, guys, we got the SX6S, SF, SFG. So now we need to substitute here. And if we substitute here, so it will be, we can write S6X, it is equal, this value is 6.6796 minus SF is 0.6492 over, it will be SFG, that means 7 point, okay, where it's gone, okay, just a second, yep, okay, we just lost it, so let me write it down. Oh no, it's come back. So it's 7.4996. So it will be, the quality, it will be 0.8041. So that's actually the percentage. You know the quality definition. We got X6s. And now what we will do, we will calculate the Hayes 6s, because we are looking for this value, the enthalpy, and it is actually the Hayes F plus the quality X6s and Hayes FG. So Hayes F is equal on 91.81. I will show you, and this is 0.804 and it is 2392.1. So it is 2115.3. You look, we actually used table A5 here, table A5 here. So table, when we use table A5, you can see for enthalpy, yeah, this is the values, all these values. Alright, so we got all of these values. So that means now we can calculate the work output per turbine. So work output per turbine, you know the formula, it was eta T has 5 minus has 6s. So now we got has 6s here. So eta T, you know, it was 87%, so 0.87, and has 5 we can simply get from the table A6. You know, it is actually 358.3.1 and minus this is 2 on 5.3, so it will be actually 1277.0 kilojoule per kg. So that means we got both. So that means now what is the net work output? So the difference between these two, so 1277 minus, we calculate earlier for pump, it is 19, so it will be 1258.0 kilojoule per kg. So we got this. And now, you know, if we want to calculate the efficiency, so this is the net work output and the heat in. So net work output we got how much it is, we got 1258, and the heat in, how we will calculate the heat in? Look, heat in actually here is you guys know, if you look at this this TS diagram, or if you look at this schematic, this is the boiler, so it is coming here this end. So if we calculate the enthalpy difference between this 0.3 and 0.4, so that means the H3 and H4, the difference between these two, it is actually the heat in. So we can say it is actually the H4 minus H3. So the H4, we can, H4 is, what is the condition? Look, 15.2 ampere, 625 degrees centigrade. So it is H4, it is actually in the superheated region. So if we use table A4, so this is 1258. So for H4 we will use table A6. So superheated table. So it is 3647.6. I said this is table A6. And for H3, this value is given in the question. It is 160.1. So the efficiency, it will be 0.367, or you can say 36.1%. So this is actually the efficiency that we are looking for. It's a long calculations, but I tried to explain, but I was a bit quick, but still I believe you understand, and we'll even discuss it during the lecture as well, so you can also follow the lecture video. So now the second part of the problem is it asked about the amount of the power produced by this power plant. Okay, so actually the question is asking about the net power output for mass flow rate of 15 kg per second. So this is very simple, guys. If we it is actually the net power, so the net power that produced for given mass flow rate. So if we multiply the mass flow rate and the net work output, then we'll get the power produced by this power plant. So yeah, that's easy. So the mass flow rate is given 15 kg per second, and then total work output we had 51258 kilojoule per kg. So we have, it is 18.9 kilowatt. So that's actually the second part of this problem. So what we did, guys, here we need to use the table again and again. We need to do a lot of calculations sometimes, especially when it is in the the mixture region. Then you need to calculate the quality, and then you need to use those formula again and again for each and every problem. So all of these problems, especially for whole cycle, yeah, you will see it is lengthy problem, but if you can understand, then yeah, it should be easier. So we'll discuss it during the lecture as well. So that's it